Welcome back. Alright, it's finally time for the rubber to meet the road. Let's peel out and check out example 1. So example 1 says find the volume of the solid generated by revolving the region bounded by the following lines and curves about the x-axis. And we've got y equals the square root of x, our very familiar friend. Then we've got x equals 0, which remember is the y-axis. And then x equals 4, which is the vertical line over there at x equals 4. So that's this line right here. And y equals 0, which is the x-axis. That's where all the y values are 0. So the region is shown in figure 17. It's this region that's bounded by really the first and the third and the fourth curves. The first curve is just making sure that you know that on that side we have a bound. Kind of giving you a hint as to what our interval is going to be. All right, so there's our region, and what we have here is a little snapshot of one of the cross sections of that region. Now we're going to make a volume of a solid generated by revolving the region about the x-axis. So if we think about revolving this about the x-axis, well, this part of the region, if we just think of this as like an infinitely thin rectangle, this part of the region, when we revolve that about the x-axis, is going to map out a circle. Now, we're looking straight at the xy plane, but if you had tilted it just a little bit, you would see that it would look kind of like a circle, like a disc. And so I drew it like an ellipse, but it's supposed to be like a 3D kind of version of the circle. All right. So if we took this circle and grabbed it out and put it flat on the paper, it would look something like this. A circle, or as best a circle as I can draw. So our goal is going to be to find the area of this circle. Now, what we're going to need to find the area of the circle is the radius of the circle. After all, the area of a circle is pi r squared, where r is the radius. So what is the radius of this circle going to be as a function of x? Remember that every time x changes, we get a different circle. We have smaller circles over here to the left. We have bigger circles over here to the right, because the radius, the radius of the circle is going to change based on what this function is. So what is the radius of the circle going to be? So if you said delta square root of x, that would be correct. It's whatever the y value is up right here. On the top here, which is given by the square root of x. You can check that. Like, let's say we moved the x all the way over to the right, where we have x equals 4. Well, there we would expect the circle to have a radius of 2, right? Radius of 2. There's a little tick mark right there for a y value of 2. And indeed, if you plug in x equals 4 into the square root function, you get the square root of 4, which is 2. I mean, that's what gives you this y value right here, which then is going to represent the radius of the circle at that particular x value. So in general, the radius of these circles are going to be given by the formula, the square root of x. Okay, so I'm going to write that out. Cross section has a radius of the square root of x. All right, well, let's write up what the area then of these circles are. They're going to be pi times the radius squared. I'll write that out. Where the radius is the square root of x. Now the square will undo the square root of x, at least for positive x values. This will be the same thing as pi times x. Let me just write that little note in there. This is assuming that x is greater than or equal to 0. but it is, you know, for all the x values across our interval, this is true. So our area then of our circles is going to be given by this formula pi times x, it turns out. Okay, so let's plop that area into our formula that we came up with for the volume of the solid that's generated by revolving this whole region here about the x-axis. So what we do is we take the integral across our region, or across our solid. So that's going to be from x equals 0 to x equals 4. And you can think of this as like adding up all of these areas of these circles as x goes from 0 to x goes to 4. So you're adding up like the areas of all these circles. Technically, you're adding up the volumes of these infinitely thin cylinders, but you can think of those as circles if you want. And so what goes inside of our integral is the areas of those circles, and then we have the dx to provide the infinitely thin width of those of the cylinders that are made by the cross sections. Okay, so we're going to put, just generally speaking, this is going to be the areas of the cross sections, and then we'll plop in what we found the areas to be, which was pi x. Oops. And I will pause because everything just crashed. I'll be right back in a second. Okay, I'm back after everything crashing. Let's continue. So here we're going to integrate pi x. And remember that pi is just a constant. We could pull that out of the integral if we wanted to. Or just kind of leave it there and think, okay, what's the integral of x? And x is going to be x squared over 2 when we integrate that. Find the antiderivative. Then we'll plug in the 4. So we have 4 squared over 2. And when we plug in the 0, we'll just get 0. So this is 16 over 2, which is 8, and then pi. So there's the volume of the solid that's generated by taking this region and spinning it about the x-axis. This is pretty amazing that we can do this when we didn't have a formula to begin with. Now we can even think about going back and figuring out where all those formulas came from in the first place, like the volume of a cylinder, the volume of a cone would be very interesting, of a sphere. Anyway, getting sidetracked. That's it for this example. Let's call it a video and we'll move on in the next part. Thanks for watching. Take care.